Multiplying monomials. So when we start to deal with monomials and multiplying, we're really doing a lot of talking about working with exponents and powers. And we kind of have to switch gears as to how we think about things because it's a little bit different than working with our equations, which we've been doing a lot of work with solving equations. This works a little bit differently. Don't worry, the equations will come back. But this works a little bit differently. You're going to have to kind of shift how you think about things. So let's start with what is a monomial. So a monomial is a number, a variable, or a product of a number and one or more variables with non-negative integer exponents. So here comes our exponents in there, and it has only one term. So monomial, mono, it has only one term in it. So let's see if we can tell which one of these are monomials or not. So 17 minus c, this is not a monomial because it has subtraction in there, or adding the opposite in there. So it has a version of addition. Remember, this is only multiplication that we're including as part of our term here. B, 8f squared g. This is a monomial. I have a number, and then I have some variables that I'm multiplying them all together here. We need non-negative integer exponents. I have an exponent of 2 here, and I have an exponent of 1. Everything has an exponent on it. If it's not there, then it's a 1. The 8 has an exponent on it too. That's a 1 also. So again, we have all non-integer exponents. We're multiplying numbers and variables together. We're good. It's a monomial. 3/4. Yes, that is a monomial because it's just a number. So we're only dealing with numbers here, so this is a monomial also. Not very exciting, but it's a monomial. And our last one, 5/t, and this is where things get kind of weird. We can divide with a variable and have it be a monomial. There's nothing wrong with it, we just don't think of it as a monomial. And again, this goes back to our non-negative integer exponents. We'll get back to why that doesn't work in this particular way, but if I'm dividing by a variable, it is not a monomial, so not a monomial. All right, let's actually get into some application with our monomials. So we're going to start multiplying some monomials together, and we want to see how those work and how we can actually think about how they work if we kind of really look into the detail of them. So we're going to start with product of powers. To multiply two powers that have the same base, add their exponents, and we're going to keep that base. So just a reminder that it has to have the same base in order for this to work. So first what I'm going to do is I'm going to kind of show you what this looks like if I imagine that we're in a microscope and we're looking at it really, really detailed. What does it look like? So r to the 4th times -12 r to the 7th. So if I kind of really look at this really detailed and I explode it and see what does it look like if I break this down, r to the 4th is r times r times r times r. -12 is just -12. And then r to the 7th is r times r times r times r. There's 7 of them. I bet you get the drift here. So this is what this looks like if I break this down and I don't use these really efficient exponents and bases that make multiplying repeatedly kind of a little bit easier to write. So if I break it down, this is what it looks like from the long version. So if I wanted to simplify it, the -12 has to do its own thing because that is a base all by itself. But the r's, since this is all multiplication, they're the same base, I can just group them all together as repeated multiplication. There are 4 of them here, there are 7 of them there, that gives me 11 of them, so that's r to the 11th. The shortcut, which we talked about, is keep the base and add the exponent. So the 4 plus the 7 gives me 11. It has to be the same base. If they're not the same base, this pattern doesn't work. Because notice I've got a bunch of r's here. That's the only reason I'm rewriting this base as an r, and there's 11 of them, so we get 11. I am not expecting you to write this out, but if you get stuck kind of imagining what this would be if you exploded it, might help you kind of figure out some of the pieces. So this next one, I'm not really going to expand it like that. 6c d to the 5th times 5c to the 5th d to the 2nd. So I'm going to put together bases that are the same here and combine them to simplify this. So I have my 6 and my 5. Now those are not like bases, but they're kind of the bases that are just have numerical bases, and they don't really have anything in common with the rest of these variables. My c and my c to the 5th, I'm going to group them together. Please note that the c is c to the 1st power, so it does have an exponent. There's a 1 there. We don't usually write that 1, just like we don't write the 1 when it's a coefficient, or a 1 when it's a denominator. There's a lot of 1s that we don't generally write. There's a 1 there. And then I'm going to put my d's together, d to the 5th times d to the 2nd. So again, 6 times 5, that's just old school 30. Nothing fancy there. Now my c to the first times c to the fifth. If you imagine it blown out, I've got c times, and then there's 5 more c's, which gives me c to the sixth. So 1 plus the 5 gives me the sixth. Keep the base, which is a c. Here I have my bases of d's. I can clump those together. I have 5 of them and then 2 of them, which gives me 7 of them altogether. So my simplified version of this product is 30 c to the sixth d to the seventh. All right, let's check out some more applications of our monomials and multiplication. To find a power of a power, multiply the exponents, and to keep the base. So again, here I'm kind of building one on top of the other. I've got 2 to the third power, that's to the fourth power, and that's to the fifth power. So I'm going to blow this up a little bit. What does this look like? I've got inside here 2 to the third to the fourth power. So there's 4 of these 2 to the thirds. I'm going to leave that fifth power alone for just a second now. But this inside, going back to our rule from our last example, I can keep the base because they're all 2's, and I can add the exponents. So that's 3 plus 3 plus 3 plus 3. That gives me 12. So I have 3 to the 12th. And now I've got 2 to the 12th to the fifth power. Again, if I break this up, that's 2 to the 12th 5 times. And so I've got my 2 to the 12th 5 times. I'm going to keep my base of 2. But notice I've got the 12th power 5 times. That's 12 times 5. I don't need to add those all together. 12 times 5 is 60. So I end up with 2 to the 60th power. Now, to use my shortcut, I could have gone back here and done that. Base of 2. 3 to the 4th is 3 times 4. That gives me 12. And then the 12 times the 5 gives me 60. So I'm not expecting you to write all this here, but I'm kind of writing it out in the expanded version so that you see what that actually represents. All right, let's do this next one without writing it out the long way. C to the second, to the third power, to the second power. Now notice for this one, I started inside and worked my way out. We could go the other way. So I could leave the c to the second alone for a minute and do my to the third power to the second power, that's to the sixth power. And then c to the second power to the sixth power is c to the 12th power. So I end up with c to the 12th power. All right, last rule for right now, power of a product. To find the power of a product, find the power of each factor, and then multiply them. So we're doing the power of a product. So this is the product inside. I have 3 variables multiplied together, and I have a power of that product. Now what does that mean? What that means is I'm actually, in this case, kind of powering each of these bases. I have a to the second, and I'm going to cube that. So a to the second cube. I'm going to have b to the first power, and I'm going to cube that. And I have c to the third power, and I'm going to cube that. It kind of feels like the distributive property. It is not the distributive property, but that's kind of what it feels like. So I need to apply this cubed to everything here. Another way I can think about it is I'm taking a squared bc squared cubed times a squared bc cubed times a squared bc cubed. So then I can regroup from there. That works too. So here, going back to my power of powers here, a squared to the third power is a to the sixth, b to the first to the third power is b to the third, and c to the third power to the third power is c to the ninth. So this is what I end up with. Again, we want to make sure that when we're done, we have each base written only once, is how we want to finish that off. All right, and our last one, negative 5x squared y to the second power. Again, I can break this up, negative 5 to the second power, I want x squared to the second power, and I want y to the second power. As you get more comfortable with these, you don't need to write this out. You're welcome to skip right to this one. That's fine. But I want to kind of write it out so you see what it looks like. So this is a negative times a negative, which gives me a positive. So I end up with positive 25. X squared to the second power, which is x to the fourth. And y to the first power to the second power, which is y squared. So we're going to get a little practice with these, kind of manipulating these rules around. And then we're going to put them into a whole big mess all together and see if we can simplify some more complicated ones. But our 3 basic rules that we work off when we're working with our powers.